Okay, welcome. So, any questions, comments before I start on the topic of the day, which is the integer quantum Hall effect and its edge states? Also, before we get started, thanks a lot for, I think most of you have settled on a presentation topic, and these are listed under the presentations pages on the Canvas site. I think with one or two, I'm still continuing the communication, and I may have lost the thread with some of you. So if your name is not on the list, please contact me in the next day or so. Okay, let's see. You can hear me, right? All right. So we're talking about integer quantum Hall states, and you can see here a semi-classical picture of electrons that that undergo circular cyclotron orbits in the bulk. But whenever you have a potential, like at the edge of the sample, then in fact there's a drift. So they really don't go anywhere, just move around in circles in the bulk. But on the boundary, they drift. This is sometimes called the E cross B drift in plasma physics. And this drift gives you quantum mechanically the edge states. Also, I realized that this equation I wrote down for a ferromagnet was not correct. I always mix this up. It's the other way around. The curl of M is J, not that the curl of J is M. That's what I saw. Let me correct that from last time. And this is the equation that tells you that if you have a bulk ferromagnet with all the electrons going in circles in the bulk, then there's a net current on the edge. Well, you know, and in an ordinary ferromagnet, there's nothing special about the current, partly because it's three-dimensional, and most ferromagnets are metallic, so there's no gap in the bulk. But in 2D, when you have an insulator with a gap, then any kind of orbital magnetism leads necessarily to edge states, quantized edge states, and a quantized Hall conductance, if they're okay. So a summary of mechanical treatment using these two pictures. Somebody has a question? So these pictures are a bit confusing because sometimes people try to draw both K-space and real space simultaneously. So here on the top is the real space picture, where you have quantum Hall infinite bar of finite width, but going infinitely in the x direction. And there's a magnetic field coming out of the plane of the board. And in this situation, what you find are right moving one band. If you have only one Landau level fifth, you have a band of right moving fermions here and a band of left moving fermions here at the two edges of the sample. The way this appears in real or momentum space is shown in the bottom. So you can view the horizontal axis here as the y-axis. And what this is telling you is that if you look at the energy levels in the bulk of the sample, they all have roughly the bulk values, which are the Landau levels, which are spaced by h bar omega c. But at the edge, all of these levels move up, and depending on where your chemical potential is, you know, you're going to get the edge states. Okay, but more precisely, and this is at least for this geometry a rigorous statement, if you take this geometry with no impurities anyway, then everything is translationally invariant on the x direction. So all eigenstates can be labeled as a function of kx. So you can view the horizontal axis here as just the kx axis. The same axis for both edges of the sample. And if you work it out, then the dispersion as a function of kx. So this is really E1, which is now dispersive, is a function of kx. And E2 is E0 is also a function of kx, and so on. I'm sorry, I guess it's conventional to call it E1 and E2. So that's the first Landau level and the second Landau level, and the energy disperses as a function of kx. And the other statement is that if you look at the current carried by any one of these states, which are labeled by the integer n, which is 1, 2, and the momentum kx, then the current carried by a state is v, which is as usual for any quantum mechanical particle, it's dE dN for the nth state divided by kx. So what you see is that in the bulk of the sample, they don't carry any current because dE is roughly independent of k. But at the edge of the sample, here v is going up, and so that tells you in the appropriate orientation that the current is going, let's say, in the x direction, which is in this case would be into the board, and on this side, as a function of k, the energy is going down, and that tells you that the orientation of the current on this side is opposite, just like the top picture shows. All right, so that's the picture, very generic picture in any finite Hall bar sample, and telling you how these edge states appear as kind of the region where the bulk Landau levels start going up in energy because of the trapping potential at the boundary of the sample. All right, so in any given system, then there'll be some chemical potential. There'll be a chemical potential mu. So this is your chemical potential, and that tells you that all these states here are filled in equilibrium. Okay, so that's the situation in equilibrium. Now we want to perform an experiment where we drive some current through the sample. So the current is going to go, in the x direction here. Okay, so the way we're going to, since it's the Hall effect, we're going to apply a voltage in the y direction and drive a current in the x direction. So what does a voltage correspond to? So a voltage corresponds now to, putting a chemical potential here. So this is, say, let's call this V right, and a chemical potential here, which will be V left. So we're going to drive the system out of equilibrium by putting a battery on it. And that's going to raise the chemical potential on the right and lower the chemical potential on the left. More formally, it's the electrochemical potential. Okay, so now you can see just by looking at this, that the states that are going to carry the current for you, which won't cancel out between the left and the right boundary, are these states here. So you just have to add up all of these states in this region between V left and V right. How many states do you have? How much current do they have? And that will give you the current. And hopefully it'll be proportional to V right minus V left, and the coefficient will give you the conductivity, or in this case, the Hall conductance. Okay, so let's just do that calculation. So that's what gives you a quantized value. So here, as I've said, you make a voltage difference with the difference between the voltage in the left and the right part of the sample. And what is the current? Well, this turns out to be the remarkably beautiful part of the computation. The current is, of course, just proportional to the velocity of each particle times the number of particles that you have. So let's see, what's the velocity? Well, we computed that on Wednesday. And there it is with the right normalization. It's E over Lx. This is just some normalization in the x direction, which won't be important, times the derivative of En over Kx. And this is an exact result that came from the Feynman-Hellman theorem in this case. So that is the current carried by any particle with some momentum Kx. All right, so you just have to add it up. Okay, so we're going to integrate this over all Kx. That's the integral over Kx. And then I have to just multiply it by the Fermi function. Why am I calling n? It's usually called f in this course. So I'll have to fix that typo. That's f, that's the Fermi function. So it's the Fermi function of the nth orbital. Really, this should be, sorry about this. I'll fix that. It's just f of En of Kx. Okay, now this function here at 0 temperature, either 0 or 1. And really, this says that I should really just integrate, only between these two values, the chemical potential. Because below that, the two ends will just cancel out. So if I just only integrated that window, I have to do this integral dkx, den dkx. Well, that's the world's easiest integral. And that simply gives me the difference in energies between the two ends. Basically, it gives me, I'm doing the integral from here to there. And I basically get the difference in energy between that point and that point, which is nothing but the voltage. So there's the answer. The whole dispersion, don't even need to know the dispersion. The dispersion could be anything in between. There could be impurities lying around here, and the actual dispersion could, maybe be looking like that. You don't know because of the impurities. It doesn't matter. You just integrate it over. All that matters when you do the integral is the difference in the chemical potentials on the left and the right. And therefore, you get then, you just integrate over all the occupied regions. So F is 0 elsewhere, and F would be non-zero from this value of K to that value of K. So that's what you're integrating over. So this is just equal to 1 for in the current carrying region. All right, and there it is. So and you would get this another corresponding contribution for each Landau level that crosses the chemical potential. In this case, only one. If you were up here, you'll get one contribution from each of the levels, and therefore the Hall conductance is quantized. It's really quite remarkable how simple the final result is, and all the dependence on the velocity. We didn't know what V bar was exactly. We didn't know what En was. It just drops right out. Okay, so that's really the essence of the quantization of the Hall conductance, is the existence of the edge states, and the fact that transport of particles in 1D is really very simple. Okay, so this should also, so there is, a lot of people have tried to exploit this and try to convert this very simple picture to a more realistic picture of how an experiment is done. So in this picture, I'm imagining that, I just somehow, I don't know how, but gently change the chemical potentials on the two ends. But to actually change the chemical potential, I will have to put in leads, which will then give me another reservoir of two ends. And then I'll have to put leads in the front and the back to measure the current. So you really have to do a 4-probe measurement. So the actual geometry, would look something like this. I would have 4 reservoirs. So here I have a reservoir here, I have a reservoir here, and a reservoir here, and a reservoir here. And the current will be, going from here to the reservoir and out from the reservoir to this one, and so on and so forth. So this kind of analysis has been done very carefully. And there's a very nice paper by Butiker where he goes through this analysis very carefully. That's reference 1 right here. And in the end, when the dust settles, what he shows very nicely, which I will not reproduce here, that the conductance, the Hall conductance, essentially reduces to the ordinary conductance in 1D of this wire. You can just think of the edge as a wire that's carrying some current. And for that wire, you compute the conductance. So you have a one-dimensional view of the sample where you have, let me make a picture here. So you just have a wire. Okay, so let's draw this here. So here's our 1D wire. This is really a stand-in for the edge of the sample, and the electrons are just flowing along this wire. And here there's a reservoir. So if I make this axis the energy, and this is the direction of flow. So here's a reservoir which has, fill states over here on this side. And on this side is a reservoir with a lower voltage. So I'm not making, I should use a different color to represent the energy axis. So basically electrons are coming out. Let me erase this here. So these are the reservoirs. This is the x direction. And the electrons are coming out of the reservoir from here with some velocity v bar. And the current, and this distance here is the voltage. So basically you have some imbalance. This is the Landauer picture of transport. You have two reservoirs connected to a wire. One reservoir is slightly higher energy. And basically the net current is all the current that's being emitted by one reservoir, which then travels freely without any collisions from one reservoir to the next. So this was a picture of transport that Landauer proposed, which initially seemed extremely surprising because we always think of resistance as having to do with dissipation. And you would naively think if you just had a perfect wire with no scattering, the resistance should be zero. But in fact, it isn't in 1D. And really the correct way to understand is that once the electrons moving at this velocity v bar land on the right, they fall into the second reservoir, and that's where the dissipation happens, when they equilibrate rapidly with the leads. So all the dissipation happens in the leads, and the net current that's carried is just the current in this window of energies. Now that's something we can easily compute, and that's what's done here. So what is the current? Well, the current is E times V of K. Sorry, E times V, because each have the velocity V. And how much and which window of energy should we put in? Well, if here's their dispersion K, this is the K direction. And then this energy here, we take to be, let's say, this point, that's the point A. And the energy here, we take to be this point, let's say, whatever it is. And so we simply have to count the current carried by all the electrons in this energy window. So this distance is V, okay. And this from here to here is V. So that's exactly right here. So there's this is non-zero in this interval when V bar K is greater than 0 but less than EV. Well, if you do this integral, again, the V bar cancels out, and you get precisely the Landauer value for a conductance of a perfect wire. It's E squared over H. And that's really the reason for the quantization of the Hall conductivity, because it's just related to the conductance of the perfect wire, which has no backscattering on the edge, because there are no states that move backwards. I mean, if you take an ordinary wire, the states moving in both directions, and electrons can get backscattered, and it's the backscattering that gives you a resistance that's higher than predicted by this perfect wire, which has E squared over H. Okay. All right, so hopefully now you're starting to feel a little better about the origin of the quantized Hall conductance and how it's related, which is a special feature of 1D of the fact that when you compute the current in any energy interval in a regime where the dispersion is linear in K, then the velocity just cancels out in the conductance. And that's the key thing that makes this whole thing work, the cancellation of V in an integral like this. Okay, I mean, if you want one more step, this is the integral from E times dk over 2 pi times the current, which is E times V bar, but this goes from 0 to the voltage divided by V. And that just gives you, forgetting e squared over 2 pi times v. And the 2 pi comes from this 2 pi here. Of course, the h bar, we fudge the factor of h bar. We never remember h bars just by just making sure the units come out right. You put that many factors of h bar. But the 2 pi you have to keep track of, and that's where it comes from. Questions? All right. Then, what else do I have to say about the integer quantum Hall effect? Okay, this is just preparing for when we get to the fractional case. Maybe I'll spend a little bit more time on it then. So we've done a calculation of the conductance using this theory for the edge. And it's a perfectly good theory because it is the actual simplest way of understanding what's happening at the edge. But we showed in the previous chapter that this free fermion theory is exactly equivalent to this chiral boson theory of a boson that's moving, dispersing also linearly, and has this Lagrangian and corresponding Hamiltonian and commutation relation that I won't bore you with. And it would be interesting to see how this result comes out also in this so-called chiral Lagrangian liquid theory. And the reason is that when we go to the fractional case, 32 will no longer apply, but 33 will just have a very small change. So we can redo the calculation very easily using this theory, but this will not apply at all because we will not have free fermions on the edge of the sample. But we will have free bosons, strangely enough. Okay. So what is the bosonic way of getting this answer? Well, you basically, again, you take the one-dimensional point of view and you just do a straightforward calculation of the current given some voltage. So you take some voltage in 1D. So now again, you have some sample here, which with one reservoir some voltage, and then eventually on the other reservoir it goes up. This is X. This is some voltage or equivalently some potential. And because of this potential, you try to figure out the current. So you just do a linear response calculation. If you apply a potential V, what is the current? So this you just do by the standard linear response formalism. The only, there should be a 0 over here. I'll fix that. There should be a 0 here. So this response function is basically the current correlation function. I mean, sorry, it's the current voltage correlation function. With the voltage couples the density, so it's the current density correlation function. So what is the density? Well, we remember the density from our Lagrangian liquid days. It's just this number. Go back and look it up in the previous chapter. And by current conservation, this tells us that the current is the time derivative of phi. So we just need the 2-point correlation function of the density with phi. Okay, that's very easy to compute because the theory for phi is just a Gaussian theory. And in the Gaussian theory, what is the propagator? Well, this is k squared, even if Fourier transform, and this is k times omega. So what we know is that phi in Fourier space is basically 1 over, forgetting the 4 pi's and all of that, which you do have to keep track of. It'll be v bar k squared plus I omega k. Okay, the omega k comes from here and the k squared comes from there. So that's the phi propagator. But then you also have here one gradient from here and the one time derivative from here. And so that gives you this with all the signs done properly. Okay, so that's the retarded propagator. And now I have to analytically continue and then take the limit omega going to 0 and do the integral. All right, so that's a little bit tedious, but it can all be done. And what you find is that you get a one-sided response where the current at one point only depends on the voltage behind it, which makes sense because it's a chiral system. The response here only depends on electrons coming in from this side. And if you just compute the current, it's exactly the Landauer value again.
Sabir,
yes.
Is there a diamagnetic term in this case because the action is second order in the gradient of phi?
Well, yes. So, I know I worried about that a lot. I think the way to think about this is that this boundary theory is anomalous. It's not really, it's got a anomaly, which I'm going to talk about in a minute. And I think the safest way to do the calculation is to, so it's not gauge invariant on its own. It's really the boundary part that's gauge invariant. So the safest way to do the calculation is to find the operator in the fermionic language and then write them down in the bosonic language. Yeah. This question kept me up for the past week, and I think that's the answer right now. Yeah. Okay. Yeah. I think just wait. Just let me just cover the next section, and then we can come back to this point. Okay, but that's a very good question. Anyway, so what I've done here is just taken the expression for the current that we had, so the density that we had from Bosonization theory, and then deduce the current by conservation. So there can't be any corrections to that. Current has to be conserved on the boundary, and then you compute the response function as Gaussian theory. Yeah. Okay. Now, right. I think these are the correct expressions. Okay. All right. So now let me turn to a rather subtle argument, which will be really the key to many things we're going to talk about in the next week or so when we get to the fractional and more subtle cases. But even here, this argument is really quite important because it really shows us that the results we've been presenting so far for the edge states are very robust. They're just, they might, and we can kind of see that from the structure of the arguments, but still, we made the arguments in rather special geometries. But you might worry, well, if you had a more complicated geometry, maybe there's some situation in which the edge states don't appear, and so, and the conductance is not quantized. I mean, so there could be, it's not really a rigorous argument, but you can make it more rigorous by the idea of anomalies, which is now I'm going to try to present my understanding of. And maybe, I don't know if Juven is listening, but hopefully this will make Juven happy. And correct me if I make any mistakes, of course, Juven. All right, so we're going to present what are called anomaly inflow arguments, which really emphasize the topological nature of these edge states. Okay. So the way these arguments go is really by trying to understand gauge invariance with respect to the external perturbations, the voltages in the magnetic field that you apply, the physical perturbations, in a very careful manner. So here the perspective is that we don't think of electromagnetism, ordinary electromagnetism in lab, as some theory with its own dynamics. It's just, we just imagine that the dynamics of the electromagnetic field is so rapid and so high energy that we don't have to worry about it. We just imagine that we have some knobs in the laboratory, and with those knobs, we can change the value of the electromagnetic gauge field A mu to be anything we want. And we want to understand something about this theory in which A mu has been fixed by us in the lab by magic. We want to see how the electrons respond to this A mu. So if we go back to this original Hamiltonian that we considered, And these arguments, you could even add electron-electron interaction that they will still go through without any change. So we have some general Hamiltonian here of some vector potential and a scalar potential, giving you this Hamiltonian we looked at. We just take some very general Hamiltonian like this of electrons in some bounded region of space. Okay. So in that region, it's a perfectly well-defined Hamiltonian, and we are certain that that theory of the electrons is completely gauge invariant. There can't possibly be any problem with this. It's just everything is finite and there's no divergences anywhere. It's just a bunch of electrons in the presence of an externally imposed gauge field. So let's imagine we can completely solve this problem, at least in principle. So what does that mean? So we represent that by the statement that we compute the partition function as a functional of the gauge field. Okay, so you give me some gauge field, mu. I couple a bunch of electrons in them, and I just figure out all the eigenstates at any temperature. I just do the whole thing. And that gives me something I'll call the partition function of the electron, which is a functional of the mu. And mu could have any space or time dependence whatsoever. So principle, I know that I can compute this, and it's a perfectly well-defined problem. So the statement is that whatever the z of mu, which in general is very hard to compute, it must be gauge invariant because it's a well-defined problem of electrons in a bounded region of sample. So this must be true. So you give me a z of mu, some functional, and I check that mu plus d mu lambda doesn't change the value of z of mu. That must be true. Okay. So now we're going to try to compute and check this answer in some approximate theory. So let's say we're far from the boundary, we're in the bulk, and so we're going to try to say, well, there's a bulk contribution and a boundary contribution, and these are roughly independent of each other, we hope. So we can just factorize this pattern integral into the bulk and the boundary terms. Now, the advantage of doing this is we already computed the bulk. So what was that? Well, that was way back here. What we showed was that if you had a sigma xy, and we discussed this a little bit more in the discussion section the next morning, I think. Yeah. Right, maybe I can review this again. So we computed the Hall conductivity and found it was non-zero. It was equal to this. I mean, I didn't do the details of the calculation, but this is what we claimed. And then we said that this implies that the bulk action is equal to this Chern-Simons term. That was a bit quick, so let me review the arguments as we went through in the section, in the discussion session. Right, so let's think of it this way. So here's the partition function I was just telling you about for the bulk. I integrate it out and I get some written, I've written in terms of an action. Now suppose I have this action. This is a very useful thing because now I can compute the current. The current is just the expectation value of the current itself. And the current is just the derivative of the action with respect to the vector potential. Well, Lagrangian, but as you learn in electromagnetism, at least when I teach it. So you take the average of this with respect to this action, and then you can see this is d by dA of the log of the partition function. So that's the current. So this tells me, but I know what J is. I just told you it's sigma ij times the electric field, but the electric field is dE dt. So I use that, and up to ignoring factors of I and so on, it's omega times sigma times A. Okay, so now I know something about this effective action. It's one of its derivatives gives me this term. So that tells me one choice for the effective action, which will make this work out right. Well, maybe I'll throw in a factor of 1/2 here, will be omega times AI AJ times sigma IJ. Okay, but that's not fully gauge invariant, so we can try to guess how to make that gauge invariant. And that's where the Chern-Simons terms comes in. We just noticed that this thing is at least gauge invariant in the bulk. If you just consider this term, which is ax d tau ay, and complete it to this term here, where this ax d tau ay appears here and also appears here. And the others have to be there. Without putting the other ones, you will not be invariant under gauge transformation in the bulk for arbitrary time and space-dependent gauge transformations. So that's how we obtained this effective action right here for one Landau level. Okay. And how did I get the 1/4 pi? Well, that simply comes from writing this for one Landau level for nu equals 1 as e squared over 2 pi h bar. The h bars we never keep track of. So this 2 pi gives me this 2 pi, and the other 1/2 comes from this 1/2 here. Okay, so that's where the 1/4 pi comes in. Okay, so that is the partition function of a single Landau level, at least for low energies, in the presence of an arbitrary gauge field. It's the exponential of the Chern-Simons term of the electromagnetic gauge field. All right. So I know what Z bulk is right here. Okay. And now comes the key point, and this is the anomaly. So this Chern-Simons theory is anomalous, at least on any finite region with an edge. And the reason is that if you do a gauge transformation, do a gauge transformation of this, as I mentioned last time, the bulk contribution is gauge invariant. But to establish that the bulk contribution is gauge invariant, you have to do an integration by parts. And whenever you do an integration by parts, there's a surface term. So there's a contribution, contribution, say at y equals 0, which is only an integral over two space-time coordinates, x and tau. The y coordinate has been integrated over, which depends on lambda times, in fact, the electric field on the edge. So the bulk contribution is not gauge invariant. Okay. If you take the system and put a boundary on it, there's a term that's not gauge invariant. So now we have a problem because we know the full partition function of the theory must be gauge invariant. And this part is not. This part has an anomaly. So that must mean the anomaly must be eaten up by the boundary. It's kind of a more physical way of thinking about it. You can think of a gauge transformation, kind of a large gauge transformation, as putting a winding. So imagine you do a gauge transformation with lambda winds by 2 pi as you go around the circle. So what you're doing right now is inserting a flux tube in the center, because then the winding of lambda is by 2 pi. So when you insert a flux tube in the center of a sample, that has because you insert some magnetic field, current will flow out. So charges flow out because there's a sigma xy. Or another way to put it, when your rate of change of flux causes an electric field in this direction. If you put an electric field in this direction, that causes a current to flow in that direction. So inserting a flux tube causes current to flow out. And where does that current go? Well, those charges have to go to the edge. So the change in the charge at the edge must be due to how much charge is flowing out. Although that's a very physical way of putting exactly this statement, that the bulk is not gauge invariant and charges have to flow out. So you're not conserving charge. Lack of gauge invariance means you're not conserving charge. All right, so the boundary theory must be something that somehow fundamentally doesn't conserve charge in the presence of an electric field. So this is our claim then. If you apply an electric field on the boundary theory, it shouldn't conserve charge. And then there's a hope that the charge non-conservation of the boundary theory will cancel the charge non-conservation of the bulk in a way that everybody's happy. Charge doesn't disappear. It's just flowing from the bulk, from the boundary to the bulk when you insert a flux tube in the center, from the bulk to the boundary or vice versa. Okay, so why would you have this strange feature that the boundary wouldn't conserve charge? Okay, well, that's something very simple. The boundary theory we've said is chiral. So that's actually a requirement. You have to have a chiral theory to now have a non-conservation of charge. So let's just draw, here a boundary theory that we started the chapter on Lagrange liquids with. So say here's the chemical potential, and this is the direction k sub x on the boundary. And you have all these states here with some, let's just imagine the momentum is discrete. So these states are occupied and these states are empty. Okay, so now you put an electric field on the boundary in the x direction. There's no collision. These are free fermions, so they obey Newton's laws. So in an electric field, the rate of change of kx will be just equal to the electric field. Electron charge equals 1, h bar equals 1. This is just dp dt equals f. All right, so what's going to happen is that these particles, all of these are going to move uphill, all these occupied states. And after a little while, this state will be occupied. Maybe a few more states will be occupied. And since this is, chiral theory, which goes off all the way to infinity, as far as the boundary theory is concerned, it's not conserving charge. We are seeing particles just pop out of the vacuum when you apply an electric field. So current is not conserved, meaning it's not really a gauge invariant theory. Of course, there's no magic here. I mean, you just go back to the picture I first drew at the beginning of this lecture. This tells you what's going on. When you apply an electric field, charges are going in here and they're coming out the other side. They're coming in from here, coming out the other side, but we've forgotten about the left side. Maybe you're focusing on the right and they're coming in from the bulk. That's another way to think about it. So the chiral theory is anomalous. It doesn't conserve charge once you apply an electric field. Okay. And this tells us how to compute it. This is dk dt. So basically, this is now very easy to figure out what's the rate of change of density. So this is the basic equation, Newton's equation. I'm just trying to get the answer, by raising our hands. You can do it, of course, much more carefully, as we will in a minute. So the rate of change of density is basically the rate of change of the Fermi wave vector. And the density is 1 over 2 pi times kf. As the kf moves up, the density moves up. So that gives me E over 2 pi. So for a uniform electric field, when you apply it to the sample, the density just increases with time. With this famous equation, and that's the 1D chiral anomaly. Okay, it's the analog of wild anomalies in 2+1 dimensions or 3+1 dimensions that people are studying these days. Okay, you can do this a little more carefully. You can actually write down the equation of motion of the density for arbitrary time, space and time dependent electric field. So basically, you take the Hamiltonian for the fermions. The Hamiltonian for the fermions we learned was psi dagger Vf d psi dx, and I there, and then you put a potential, and the potential will be something like psi dagger psi times the electrostatic potential V of x, where the electric field is minus the gradient of V of x. And now you just compute the equation of d rho dt. You sit down and laboriously compute d rho dt is the commutator of rho times the Hamiltonian. You work it out, and I urge you to do that. I guess I should give you homework doing these things, and you'll get this equation, which generalizes this one to a space-time dependent electric field. So the current, or d rho dt, this is just the density d rho dt plus dj dx, is not zero. When you apply an electric field, it has an anomalous term. Okay, so does this anomaly do the trick in terms of canceling this anomaly? It sure smells like it. Even the factor of 2 pi is right, and there's the electric field. So let's just complete the argument of how that works. Okay. So suppose we are able to evaluate the boundary partition function as a function of the mu. Then just as I showed you for the bulk, it's always true that the current is that the derivative of the log of the partition function divided by mu. That's just an exact identity. Just follows from the path integral in all cases. Okay. So now if I apply this, if I change mu to d by d mu, so just apply this rule to evaluate this, take d by d lambda, well, I'll get j mu, but then I have to integrate by parts in the d mu, so I'll get d mu j mu is equal to this. So if d mu j mu is 0, which is the usual situation, then the boundary partition function has no dependence on lambda, i.e. it's gauge invariant. Okay, but we know that's not the situation. So we know that d mu j mu is equal to a over 2 pi, e over 2 pi. And therefore, this tells us something about z boundary in a mu plus d mu. It must change by this amount to give you the a over 2 pi. And I haven't checked, and all the factors of plus and minus 1 have been fudged here. I haven't had time to check them. That's exactly what z boundary is. So this term gets canceled by z boundary because of this chiral anomaly. And, all looks very fancy, but in the end, it's nothing more nor less than this very simple picture. So when you apply an electric field, charges just appear out of the vacuum in a chiral theory on the boundary. And this is simply telling us that if you insert a flux tube in the center of the sample, if you take a ring geometry, then it pushes charges out. And this is just making it sure all we're checking, and the edge states are needed to absorb that charge. It's exactly this chiral Luttinger liquid theory which has gapless excitation that can absorb the charge. And in a way to make sure that charge is fully conserved in the real sample, as this tells us. And whatever comes out from the bulk goes into the boundary. So there has to be something on the boundary to absorb these charges at 0 energy. And that's why they have to be chiral edge states. So once you have a sigma xy, I mean, really, once you have a gapped sample with a sigma xy, then you know immediately there's just no way that there can't be you can't escape having gapless excitation on the edge, because you can, by inserting a flux tube, you can create an electric field which will drive the electric charges out. So let me actually draw a picture of that. So take a geometry like this, and maybe we make a hole in the center of the sample, and then you insert a flux tube in the center. So now there'll be an electric field created this way, where the electric field will be proportional to d phi dt. And if you make phi have exactly 2 pi flux, then as we've seen earlier in superconductivity, that's equivalent to just what's called a large gauge transformation. So now when there's an electric field going out here and you've inserted a flux, then your current will flow this way because there's a Hall conductivity. So this J will be just sigma times E. So the current will flow out. You will lose charges from here and you'll gain charges over there. And this can happen at 0 energy. So there's better be reservoirs on the boundary that can absorb and emit charges at 0 energy, which means there has to be gapless edge states. Okay. All right, so that's many different physical and formal ways of seeing that these fancy anomalies are just very simple physical consequences of having a Hall conductivity with a gap in the bulk. And this boundary theory is not really gauge invariant, and the bulk theory is not gauge invariant, but in a way that the two just map onto each other. Oh yeah, one more thing here. So coming back to how I use question, you can make sure this all works out correctly also in the bosonic language. So in the bosonic language, the densities are just grad phi, as we learned in the liquid theory. And this is the commutation relation between the bosons operators. This is just a derivative of commutation relations from the previous chapter, and you get this delta prime here. And now our Hamiltonian in the presence of a potential V is the usual Hamiltonian that was there before, plus this V times rho. And now you just compute the commutator of rho with H, and within just one line, you'll immediately get then this equation here. Wait, I can even do it for you. Let me do it for you since I have a minute. So add a page over here. Okay, as usual, I'm going to fudge the factors of I and everything else. So I have the commutator, whoops, d rho dt. I'll drop the L's, is the commutator of rho with H, which is the commutator of rho with integral of dx pi vf rho sub L squared. That's V rho sub L. And if you take this commutator and you use this fact, the rho commutator is a delta prime of x minus y, the first term will give you something like Vf times rho. But because you've got a delta prime from the commutator of this with this, you have to integrate by parts, and you do the integral, and that will give you a d rho dx, so dx rho. And this will give you delta prime, and you take the integral over that will give you the electric field. So this is just the current, this is just dxj, and that's the electric field, which will probably be a factor of 2 pi. Okay, so that's what gives you this famous equation right here. Well, let me make a. So this is the key equation on the boundary on the non-conservation of charge, and that perfectly matches the non-gauge invariance of the bulk by the equations I presented to you. So this is, the simplest version of the famous anomaly inflow argument, and there are many more sophisticated versions of this, some of which we're going to meet when we treat more complicated cases. But the basic idea is very, very similar. So it's good to really understand the ins and outs in this context. Okay, so I covered quite a lot of material here, in this chapter on anomalies right here, a sub-chapter. So please read it carefully. I spent some time trying to understand it myself as carefully as I could. But if you have questions right now, please go ahead. Okay, that sounds good then. All right, so that's all I have to say about the integer quantum Hall effect for now. That, it's got a quantized Hall conductance every time you have a gap in the bulk. And this is associated with a chiral Ledinger liquid on the boundary. And the two are connected by this anomaly matching argument of the Bulk-Chern-Simons theory in terms of the external electromagnetic field, and the chiral anomaly of the non-conservation of charge of a right-moving fermion on the boundary. Okay, maybe I can say a few words in the next 2 minutes about the next chapter then. So the next chapter is still really about the integer quantum Hall effect, but in a slightly different context. I mean, historically, the quantum Hall effect was discovered, in 2D electron gas in gallium arsenide, where you put a strong magnetic field, and in that physical situation, indeed there were Landau levels. To a very good approximation, there were Landau levels with totally flat energy in the bulk of the sample with a lot of degeneracy. And that's the context in which it seemed, the theorist, the simplest context to study this. But now, we realize that Landau levels are really a limiting case of a band structure that gives you all these features, like the quantum Hall effect. And there's lots of other situations which are, quite readily solvable also, where you get a quantized integer Hall response. And these are characterized by what's called, in the case of a periodic potential, by a Berry curvature. So that's really the more fundamental property of a Landau level, which is kind of hidden in our treatment so far because Landau levels are kind of a degenerate limit. But it's revealed, as was revealed in a famous paper by Towles et al. If you consider the case where you have a periodic potential. So we are going to now look at just a generic band structure of a generic two-dimensional crystal describing an insulator and ask under what conditions can this crystal give you an quantized Hall effect. And this will be very intimately related to the idea of what are called Berry phases and Berry curvatures of the band. So that's our next topic. But let me just make a general statement here, which is what I made over here. So you may have heard about Berry phases. And invariably, if you read a book on Berry phases, it immediately says Berry phases are some phases of quantum system might pick up if you perform an adiabatic change on it. That is not a wrong statement. That is a correct statement. But the idea of a Berry phase is, I think, should be really thought about as much more general context. And the general context is you have some Hamiltonian, doesn't matter what the Hamiltonian is. Typically, we'll think of a one-body Hamiltonian, but it could even be a many-body system. And that Hamiltonian depends on some parameters, which I'm calling R, but R is not to be interpreted as the coordinate of anything. It's just some parameter in the Hamiltonian. It could be electric field, could be some trapping potential, could be almost anything. So some parameter that you have the freedom to vary. So there's some parameter space, and every point in the parameter space you've compute the spectrum. So that computation you do by diagonalizing the Hamiltonian gives you a mapping between your parameter space and Hilbert space. So at each point on parameter space you have a Hilbert space. So it's like you have many Hilbert spaces at each point in parameter space. So there's one Hilbert space for each point in parameter space, and we are interested in the relationship or the geometry of this set of Hilbert spaces. And now I'm sure there's some mathematically precise way of stating it, which I am ignorant about. This is something like called a section or a fiber bundle or something. Anyway, I just use very simple pedestrian languages. So you have a map from parameter space to a Hilbert space at each point in parameter space, and this set of Hilbert spaces has some beautiful geometry, some topology. And the next few lectures will be trying to understand the topology of this Hilbert space. And that has important consequences, including the integer and also fractional quantum Hall effects. Okay, that's the introduction to what we'll talk about on Monday then. Any questions?
Here.
Yes. Yes.
Is the parameter space here is something in K space in Brinell zone? Or
It
other?
could be anything. Right now, it will be for the case of churn insulators. It will be K space. But it could be, right now, the idea is very, very general. It could be anything. It could be, for example, if you want to consider many-body problem, it could be some, say I have a Z2 spin liquid, and I bring in some trapping potential. I trap a spin on here, and I trap a Vis-on here. So now my parameter space is the spectrum of the Hamiltonian as I move the trapping potential of the spin-on and the Vis-on. Okay, so that's a very large Hilbert set of spaces. For each trapping potential, I have a new Hilbert space. And I'm interested in the geometry of that. And that, of course, will give me the statistical phase factors and so on. So you can also interpret the statistical phase factors in the anyon statistics as Berry phases in the parameter space of the positions of the quasi-particle, for example. Or if you're talking about one electron, free electrons, then it could be the momentum of the electron, which diagonalizes the states, and then you have a different Hamiltonian for each momentum, and we're interested in the topology of that space. Okay. Or it could be a spin, just a single spin, and we apply a magnetic field, and we rotate the magnetic field from point to point. And that's a parameter space of Hamiltonians, depending on the orientation of this magnetic field. That's the simplest example, but there's a non-trivial Berry phase, which we're going to compute. Okay, other questions? All right, then. Today's Wednesday. I'm sorry. We'll talk about it on Friday. I don't know why I thought it was Friday today. So we'll talk about Berry phases and band topology on Friday then. And a reminder for the few of you who are not yet signed up, or those who have communicated with me and I lost track of our communication, please get back to me so I can have everybody's name for your presentation on the Canvas site. June, maybe due to election coming. Oh, because why I think it's Friday. Yeah. Yeah. Okay. Possibly. Okay, then. See you on Friday.